All right, let's take a look at Unit 4, contextual applications of the derivative. There's going to be two videos to this. One will be a short one where we're going to be reviewing the interpreting of the derivative. And then the other one will be linear approximations, which takes us to page 5 of this packet. So it's a little bit skip around, but it'll allow you to finish that first assignment for this unit. So recall the derivative represents the rate at which a function is changing, usually with respect to time, but it doesn't always have to be. All right. And you want to make sure that you use the phrase something like the rate of change or changing at the rate of or at a rate or something like that. But you want to use the word rate and the word change in your interpretation. Otherwise, there's a good chance you're going to get knocked off a point or so. All right, the next thing we want to make sure we do is we identify what these variables are, what they represent, or what those numbers represent, and that's all within the problem. And then finally, make sure that we use as much of the language that's in the problem as possible instead of trying to come up with our own. So number one, the population of trick-or-treaters at the WBHS NHS Trunk or Treat event is modeled by the function t, a differentiable function of the number of minutes after the event begins. So t, 17 here, okay, so t prime equals 17 is going to be the population, the rate of change. So it's going to be the population change per minute after the event begins. And 30 is the number of minutes after the event begins. Okay, so remember, rates of change are always something over something. Population per minute, feet per second, or something like that. Okay, so now what I need to do is take that information and go ahead and rewrite just a simple sentence or two describing that. Okay, so it would be something like this. At 30 minutes, again, using the language, after the event begins, the population of trick-or-treaters here it is changing at a rate of 17 people per minute. Sometimes the language can get a little clunky. All it's saying is half an hour after the event began, the number of people at this event is increasing at a rate of 17 people per minute. So at 30 minutes, so between 30 and 31 minutes, 17 new people have started to arrive at this trunk or treat. Okay. Notice I didn't do increasing. Okay. I said changing. We could have said increasing at a rate of because it's positive, and if it was negative, we could say decreasing. But I like generally sticking to the phrase changing at a rate of. All right, number two, the function C models the depth in inches of the coffee in a coffee pot t minutes after 5 a.m. Write an equation which represents the depth of coffee in the pot is changing at a rate of 2 inches per minute at 5:07 p.m. So since t is the minutes after 5 a.m., so t is 7 here, because 5:07 is 7 minutes after. All right, and c prime is 2 inches per minute. So to put that in an equation, we are going to say c prime of 7 is equal to 2. Okay. Number three, the function f t equals f of s models the time in minutes for a bowl originally full of candy corn whose volume is measured in cubic centimeters to empty at a Halloween party. What are the units for f double prime of s? So f of s has units of volume, so it's cubic centimeters. F prime of s, since this is the change over time in minutes, then f prime of s would be cubic centimeters per minute. which means F double prime of S is going to have a rate of change of cubic centimeters per minute, which again, we've talked about this before. We could label as cubic centimeters per minute squared. Hey, I prefer this one, but this one is fine too. All right, that's it for this video. We'll go ahead and pick up with linear approximations in the next one.